Okay, in this video I'm going to do this problem number 5. Prove using the definition of set equality that for all A, B, and C sets, the intersection of A minus B and C minus B is equal to the intersection of A and C minus B. Okay. To prove this, to prove set equality, I'm going to use the definition and recall the definition of set equality is that A is equal to B means, and is equivalent to, A is a subset of B and B is a subset of A. Okay? And so I need to do the same thing here. So I've got two pieces to show. Part 1 is to show A minus B intersected with C minus B is a subset of A intersects C minus B. Okay? And to show that, I'm going to prove, in other words, I'm going to show that A minus B, that an X being in, show the X being in the left-hand side intersect C minus B implies that X is in the right-hand side. A intersects C minus B. Okay? I'm also going to use the definition that A minus B is the set of all X's such that X is in A and X is not in B. That's what it means to subtract off the set B from A. It's everything that's in A but also is not in B. I've subtracted off B. So we're going to let X be an element of A minus B intersect C minus B. And we're going to show that X is in A intersects C minus B. Okay? I'll try to clean this up slightly here. Okay. Well, if X is in this, then X is in both of them, right? And X is in C minus B. If X is in an intersection, then it's in both of them, okay? And so I have that with an and sign here. And then, since X is in A minus B, X is in A, and X is not in B. And since X is in C minus B, X is in C, and X is not in B. Okay? And now we can say that X being in both A and C implies that X is in the intersection, since X is in A and X is in C, X is in A intersects C. Now, since X is in the intersection, A intersects C, and X is not in B, we know that X is in A intersects C minus B. And there I do need parentheses. Okay? And that's what we were trying to show. And so we are done with part 1, showing that the left-hand side is a subset of the right-hand side. Okay? Part 2 is going to go very similarly. I'm going to assume that X is in the intersection minus B. Part 2, show that X, show that A intersects C minus B is a subset of A minus B intersected with C minus B. Okay, let's just double check that's right. A intersects C minus B is a subset of A minus B intersects C minus B. Yeah, that's what I'm trying to do here. It always helps to keep double checking on these things. Okay, so we're going to show, in other words, we need to show that if x is in the left-hand side, then x is in the right-hand side. And let me make sure I copy the right-hand side down correctly before I proceed. Okay, there it is. So I can just see right through this. I'm going to say that, you know, if x is in A intersects C minus B, then it's in A intersects C. That means it's in both A and C, but not B. If it's in A and not B, then it's in A minus B. If it's in C and not B, then it's in C minus B. And if it's in both of those sets, it's in their intersection. That's what I'm going to do here now. Since x is an element of A intersects C minus B, x is an element of A intersects C, and x is not an element of B. So x is in A, and x is in C, and x is not in B. Okay? So x is in A minus B, since x is in A and is not in B. Similarly, x is in C minus B, since x is in C and x is not in B. So now, hence, x is in A minus B intersected with C minus B, since it's in both sets. Okay, and that finishes it off. Hopefully that helps, and hopefully you see that basically what I'm doing is I'm taking the left-hand side, I'm taking this subset statement, turning it into an if-then statement about elements, and then assuming the left-hand side, taking it all apart and coming up with where x needs to be and where x needs not to be, and then just putting these various facts together in a different order to yield the thing on the right-hand side. Hope that helps.